Okay guys, so you did a fantastic job with Newton's 3 laws in Sphero. Just a couple things I want to clear up with you. First of all, we know that a force is a push or a pull. And we know that when objects have reference points, we can go ahead and tell where they're moving. So something that is stationary could be a reference point, and it'll help you see which object is maybe moving faster or slower. Something else that we learned is that when we are measuring force, we're using the unit of measurement newtons. And newtons are really a combination of the mass times the acceleration of an object. So newtons is really kilograms per meter per second squared. Now, once you really start to know Newton's 3 laws, you can see it applied everywhere. A single example would be a rocket. In Newton's first law, which is also called the law of inertia, the rocket has the tendency to stay put unless something moves it. It could be the wind knocking it over, it could be a crane lifting it up, or it could be the acceleration as the rocket moves and pushes off of the ground. Now that pushing off the ground, that would be Newton's third law. For every action, there's an equal and opposite reaction. So as the rocket pushes off the ground pushes back up against the rocket and it's able to leave Earth. Now Newton's second law says that the force that is needed for that rocket is going to be looking at its mass times its acceleration. So in order to leave the planet, that object has to be able to escape Earth's gravity. One of the questions on the homework that caused some difficulty is the picture that showed the rock that was called the balancing rock. And this balancing rock is actually out west, and it has a small base to it with a very large top to it. And you look at it and it just doesn't look right. It looks like it should tip over. But Newton's first law reinforces the fact that an object at rest will stay at rest unless acted upon by an outside force. So it would have to take a lot of wind to really push that over, or maybe a crane or something knocking it over. But just the rock itself has the force of gravity pulling it down, and then the ground has that normal force that's also pushing back up with it at an equal amount of force. Another question on the homework that caused a little bit of confusion also dealt with Newton's law. And the question asked what would happen to the moon if Earth stopped exerting the force of gravity on it. Well, the moon is locked into this dance of an orbit with Earth, in which it's being pulled to it by gravity, but it also has the inertia of it that would be moving it away from Earth. A combination of that gravitational pull and the movement away keeps it falling basically around the Earth, and the Earth falling around the moon. The same relationship exists between the Earth and the Sun. Without that gravitational pull on these objects, the moon, the Earth, we would just drift off and move away from the Sun, and the moon would move away from us. So an object in motion tends to stay in motion. If you don't have gravity, that motion's going to take it away from us. Looking at the questions that you answered on the cards with your teams, the questions that I noticed caused the most difficulty were the questions that dealt with Newton's third law, action and reaction. So you start to see this law when you look at objects like a bird. When the bird pushes its wings down, it pushes against the air. The air pushes back up at the bird and it's able to lift through the air. The balloon was another example that a couple teams missed. When the balloon's air is rushing out from it, that pushes, the air pushing out pushes the balloon forward. So the key here is that it's going to be equal and opposite to that initial force. The other area of the card where I noticed there were some problems were the ones that dealt with calculation. So let's look first at the idea of something being balanced or unbalanced. Whenever you have numbers that are being used with an object and they're in opposing directions, if they're opposing each other, you can subtract them. Those are unbalanced forces if you get any number left over. So, for example, the helicopter, there's a force of 200 newtons pushing it down, but there's a force of 70 newtons pushing it up. So you're going to have more downward force. That's an unbalanced force. But you could have like a tug of rope competition here. And let's say that you have your 3 guys over here and you have your 1 guy over here. Let's say that 1 guy on the right side has just as much force as the 3 guys on the left. That could be a balanced force. Of course, without numbers, I'm just guessing here. But if you have numbers and they are opposing, you can subtract them. But if they are combining, then you can add them. Now, some of the questions didn't have any numbers, but they had a compass that you were supposed to use. So you have to look at the object and look at where the arrows are going. For example, this tennis ball has a force that is pushing it to the right. It looks like it's a pretty big force compared to the force that is pushing it downwards. So we know that the tennis ball is going to the east, and we know that the tennis ball is also going to the south. So the resulting force is going to move this tennis ball to the southeast. And you have to use both of those directions because it is combining to a southeast direction. It's probably more east than it is south, but you'd still write southeast. Now let's look at the forces that are being applied to this softball. You have 150 newtons that are moving the ball to the right and 150 newtons moving the ball to the left. So the net force, because they are moving in opposing directions, would be 0 newtons. So that ball, even though it shows those forces, is going nowhere. This question was a tricky one. It showed a motorcycle and it showed the direction moving 65 newtons to the right and 65 newtons to the right. So because they're going in the same direction, you would add those forces and you have 130 newtons of energy moving the bike to the right. On the car, opposing forces, right? So 75 newtons moving the car to the right and 25 newtons of energy moving the car to the left. So because they're opposing, you subtract them, and the resulting force is going to be 50 newtons to the right. And here's how it needs to be written. You'll notice that the number 50 has the capital letter N after it for newtons, and the arrow is above it showing the direction of travel. So what would that motorcycle look like? You would have the 130 for the combined forces, the capital letter N, and the arrow again pointing in the direction of final travel. Of course, they're not always going to be that easy. You could have forces pushing down and forces pushing up to deal with. This table has a combined force moving it to the right and combined force moving it to the left. What do you think the resulting force would be? Because the forces moving the table to the right combined to 80 newtons, and the forces moving the table to the left combined to 90 newtons, your result here, it would be a force of 10 newtons on the table to the left. Now, lastly, Newton's second law. This is all about calculations. It's all about either multiplying or dividing. Remember, force, which we measure in newtons, is a product of the mass of an object, which we use kilograms to measure, multiplied times its acceleration. So we're not looking at the speed of an object, like at a one given point. We're looking at its acceleration all the way through, so that's why we measure with meters per second squared. So one of our first examples that we had was the bowling pins and the bowling ball. The bowling ball was hitting the pins and it had a mass of 6 kilograms. The pins had an acceleration of 20 meters per second squared, and the question asked us how much force was being applied. Now, it's important to set up your equation to start with. F equals m times a. Then it's just a matter of plugging in the numbers. The mass, 6 kilograms, the acceleration, 20 meters per second squared, and then multiply, and know that kilograms per meters per second squared is newtons, and you get 120 newtons of force in this story problem. Now, what if we change the bowling ball mass to 8 kilograms? And we say that the force is 120 newtons still. What does that calculation look like? Take a minute to set it up. Force equals mass times acceleration. Plug in the force as 120 newtons and the mass as 8 kilograms and solve for acceleration. This means you're going to be doing some dividing this time. Does your problem look like this? 120 newtons on the left side of the equation and 8 kilograms times A on the right. You have to divide the 8 kilograms on the right side and the left side to remove it, and once you get 120 divided by 8, you're left with 15. Now, we know that we're looking at acceleration, and this is going to be meters per second squared. Let's change our bowling problem again. Let's say that we apply a force of 180 newtons and we are able to make the pins accelerate 30 meters per second squared. So we want to know just how massive is the bowling ball. Set your problem up. Force equals mass times acceleration. Plug in your number for force, plug in your number for acceleration, and solve for the mass. Does your problem look like this? 180 newtons on the left equals mass times 30 meters per second squared on the right. We have to divide by 30 meters per second squared on the right to get mass by itself, and whatever you do to one side of your equation, you do to the other side. So 180 newtons is divided by 30 meters per second squared. That gives us a number of 6, and we know that we're looking at the mass, so we're working with kilograms. 6 kilograms is the answer for the mass of the bowling ball. Now, take a minute to look at this image with all the numbers and the formula. And actually the calculation's done right there. What do you think the question was being asked for this picture? With this question, we were looking at what force was applied to move a shopping cart with the mass of 18 kilograms to an acceleration of 3 meters per second squared. The force needed was 54 newtons. Okay, last question. If a water skier is being pulled with the force of 104 newtons and they are accelerating 2 meters per second squared, what is the mass? Take a minute to set it up, the problem, and let's see if you can get it right. Were you able to find out that the skier was 52 kilograms? You have 104 newtons on the left. Mass is what is being solved. The acceleration, 2 meters per second squared. To get the mass by itself, we divided by 2 meters per second squared. That canceled us out on the right. And we divided 104 newtons on the left, and that gave us the number 52. We were looking for the mass, so we were working with kilograms.